Welcome! Geothermal energy is a clean source of energy derived from the heat naturally stored in the earth. Geothermal energy has been known for a very long time, and more than 2,000 years ago, Chinese, Greek and Romans and many others were enjoying thermal baths and hot springs. Hot water was also of great importance for medical purposes and since more than 150 years as a source of chemical components for industry. Since the beginning of the last century, very hot waters from geothermal systems are used to produce electricity. Very special conditions are needed, which we'll look at in a later stage. In the last decades, geothermal energy is increasingly used also for heating. This trend will continue because waters for heating do not need to be extremely hot, and therefore well-suited settings are common. All in all, geothermal energy is considered one of the key components of the energy cocktail which will support our societies in the next future. Think at Iceland, where only transport uses fossil sources. This is what a valid geothermal system looks like. In principle, it's easy. We need some heat, a good reservoir along which water can flow, and the fluid itself. Note that the water recharge and discharge can be fully natural or driven by humans. Good predictions of the three components of the system are obviously key for the scientific, technical, and eventually economic success of the project. The first component we look at is heat. One fundamental source of heat derives from the fact that the Earth is cooling, which results in heat being transferred from the central parts of the planet to its surface. For the time scales we're interested in, we can assume a steady state. The resulting planet-scale geothermal gradient is shown in the plot. You can see that temperatures in most of the mantle, from the core mantle boundary to the base of the lithosphere, are fairly constant. This is due to the vertical movements of mantle rocks driven by mantle convection. The portion of the mantle experiencing significant convection ends at the lithosphere-asthenosphere boundary, which we know it is an horizon characterized by temperatures constant of about 1300 degrees. Assuming that the asthenosphere is an isotherm surface, that the Earth's surface is also roughly at constant temperatures, that all the rocks between have the same material properties, then temperature changes between the two surfaces will follow a linear trend. The lithosphere, however, is not composed only of mantle rocks, but also of the crust. And the crust has a lot of granites, or, more in general, rocks with a high portion of radioactive minerals. The resulting geotherm, therefore, predicts higher temperatures. A typical average gradient in the crust will be between 20 and 30 degrees per kilometer. From a thermal point of view, the lithosphere is then defined by the two isotherm surfaces, the LAB and the surface of the Earth. Considering the heat equation and making the necessary assumptions of thermal properties, you can establish a link between the lithospheric thickness and the heat flow Q, which can be measured at the surface of the Earth. We conclude that heat flow is a proxy for thermal gradient and therefore for the depth of the lithosphere-asthenosphere boundary. Assuming representative values, you obtain that the average represented heat flow in normal conditions is about 60 milliwatts per square meter. This can be used as a reference to identify warmer than normal regions and colder than normal regions. The map of heat flow in the picture shows patterns which are correlated with the tectonic features we have known before. The hottest places are clear the mid-oceanic ridges, where new oceanic crust is being created. Fairly hot are also subduction zones, such as those around the Pacific. Looking in more detail, you can see warm regions in Western Europe and along the East African Rift. The regional thermal field discussed above is at places affected by local disturbances which dramatically increase the geothermal potential of the region. The most important of these are magmatic intrusions, Considering the melting temperature of magma of around 800 degrees, and assuming that it is in place at 10 kilometers depth, you can predict a gradient of 80 degrees per kilometer. And one of the most famous geothermal fields, that of Larderello in central Italy, the geothermal gradient above the Pluton is even more than 100 degrees per kilometer. Combining this geological information, we can predict areas potentially interesting for geothermal energy. Rifts. Here, the lithosphere-asthenosphere boundary is shallower than the surrounding as a result of extension tectonics. In addition, rifts are often associated with volcanism and magmatism. This is particularly the case for Iceland, where the mid-oceanic ridge is exposed with its intensive volcanism. Subduction zone, where high temperature are present just on top of the subduction zone and is associated with intensive magmatism. Typical places are New Zealand and Japan. Once you have the heat and the right temperatures, you obviously need a reservoir which is permeable enough to contain the water and to let it flow. Primary porosity is commonly present, but is often not sufficient to guarantee enough flow. Fracture porosity is of great importance in geothermal systems, especially those at high temperature, as you will see in the next clip. Note that the most important characteristic of fracture is the aperture, which among others depends on the orientation of the fracture with respect to the stress field. We have now reached the last component of the geothermal system, namely fluids. These can have two different origins and therefore compositions. In sites where magmatism is important, there are abundant fluids generated by the degassing of the magma body. These fluids are hot, loaded with very special minerals, and chemically very aggressive. When they reach the surface, they form fumaroles or even geysers. On the other side, precipitations can enter the system from the surface of the Earth and migrate downward until they are heated enough and start moving up again. Mixed water patterns are common in high-temperature geothermal systems. Your role as a geologist is a very important one. Similarly to what mentioned in previous clips, the core of your mission will be to develop a hydrogeological model as correct as possible, inclusive of geometries, physical properties, and their uncertainties. The better you model, the more efficient and sustainable will be water management. Welcome! After having looked at the main components of geothermal systems, we want now to devote our attention to how geothermal fields are discovered and how they are exploited. Eventually, we will mention some of the technical challenges facing geothermal energy. With increasing need for clean energy and with technological progress, the spectrum of settings and places suitable for geothermal energy has substantially expanded. Systems characterized by very deep aquifers and/or by low temperatures, which were considered as useless until a few years ago, are now fairly attractive. Now, letting aside the simple and very shallow borehole heat exchangers, we make a distinction between low-temperature systems, where heat is extracted from the aquifers, and high-temperature systems, where very hot water and/or steam are used to produce electricity. As a result, geothermal energy has now a very wide range of applications. High-temperature geothermal systems are characterized by having very high temperatures, typically with gradients of more than 100 degrees per kilometer. Such abnormal values are always associated with magmatic intrusion and result in strong convective movements of water which reaches the surface in natural fashion, producing fumaroles and high-temperature springs. Waters are strongly contaminated by the degassing of the intrusion, resulting in widespread precipitation of various minerals and smell. Because of their apparent characteristics, most of the areas of potential geothermal interest have already long been known, and the challenges have more to do with the exploitation than with the exploration and discovery. Standard geophysical tools such as seismic, electromagnetics, and gravity are used to define the architecture of the field, inclusive of the definition of the reservoir, the seal, and very important, the main faults. Exploration boreholes generally follow to better define the geological and the geothermal models, inclusive of the position of the isotherms. A large amount of investigation is then applied to constrain the hydrogeological model, which implies a good knowledge of the path followed by the fluids, of the amounts involved, and the temperature changes they experience. The analysis of geochemical data is also of great help. Structural studies are important to define the permeability of faults and other fractures, and are coupled with geochemical tools to constrain the trajectories followed by fluids. The field now is ready to be exploited. Extract the energy from high-temperature fields is relatively easy, as water, sometimes in the form of vapor, rise spontaneously to the surface. At the surface, turbines or other condensing units transform the vapor into electricity, which is then distributed through the standard network. Increasingly common are systems which use a secondary fluid with a lower boiling point to create steam. A major challenge to a high-temperature system is given by the chemically aggressive nature of fluids associated with magmatism, and with the high temperature at which underground operations must take place. All in all, the exploitation of high-temperature fields is relatively straightforward, and the economic challenges relatively limited, mainly because electricity can be easily transported at large distances. The downside is, unfortunately, that the high-temperature fields are not that common. Low-temperature geothermal fields, on the contrary, have thermal gradients which are only somewhat higher than normal, are not necessarily associated with magmatism, and are not related to apparent manifestation at the Earth's surface. In fact, all areas with a not too deep aquifer at temperatures above 70 or 80 degrees are potentially interesting for exploitation. In low-temperature geothermal fields, injected cold waters heat up in the aquifer and are then pumped to the surface to produce heat, not electricity. Different from electricity, heat dissipates easily, and the success of a low-temperature geothermal field depends on the amount of hot water which can be extracted and eventually delivered to the users. Correct prediction of the temperature and the hydrogeology of the system, permeability, flow, etc., is therefore absolutely crucial, as small deviations can imply the success or failure of the exploitation. The definition of the overall geometry of the target reservoir is generally relatively easy and is based on standard geophysical tools such as seismics. Typically, is then refined by exploration wells. These wells are also used to ascertain temperatures of the aquifer. Possibly the greatest challenge faced in the building of the hydrogeological model lies in the definition of the permeability of the aquifer. As we have seen several times in previous clips, this is spatially very heterogeneous at various scales. Especially in systems like fluvial sands, the lateral continuity of the reservoir can be seriously hampered by, for instance, thin layers of shales, very common in these sedimentary systems. Low-temperature fields function in a very different way from the high-temperatures counterpart, the main difference being the waters need to be injected into the aquifer and then extracted with pumps. For this purpose, all low-temperature geofields use injection and producing wells. Obviously, the communication between these wells must be very efficient. In the case where reservoir permeability is the same in all directions, then the relative position of the two wells is not so important. If, on the contrary, a region is affected by systematic fracture sets and or by fault zone, good knowledge of permeability changes is needed. As you can see in this picture, for instance, the flow between wells in A will be much easier than between B and C. Low-temperature fields produce heat, which is extracted from hot fluids. All fluids, however, have a strong tendency of cooling and will lose some of their heat during the path from the subsurface to the end users. This poses major limitation to the distance between the energy source and the consumer, typically not more than several kilometers. To be economically viable, A strong public partner must be present in order to facilitate the emplacement of the expensive infrastructure, such as pipes. On the other side, once the system is there, exploitation is cheap. In addition, and especially when targeted the aquifer is deep, the user must have a size large enough to justify the infrastructure investments. Successful examples of consumers are, for instance, hospitals and greenhouses, which need large amounts of energy over the entire year. An interesting case of geothermal energy exploitation is provided by the Netherlands, surely not what we would define as a high thermal grade region. Here, the search and use of geothermal energy is of great importance and, interest enough, was triggered by the agricultural sector, more specifically by greenhouses. Because growth curves of vegetables and fruits are strongly temperature dependent, the greenhouse sector has always used large amounts of energy, typically gas. By extracting water from aquifers of depths of 2 or 3 kilometers, they are able to save significant amount of money, triggering geothermal exploration and development in the Netherlands. Sometimes things start from a very unexpected source. Like all forms of human activity, and in particular the industrial ones, exploitation of geothermal energy has a number of challenges, which need to be addressed and included in the workflow in order to minimize their impact. The first one is the mechanic and chemical stimulation of the reservoir, also called EGS, which is needed to increase reservoir performance. This technique consists in the injection of high-pressure fluids in the rock, stimulating the formation and growth of fracture at tens of meters around the borehole. Risks associated are the possible reactivation of pre-existing faults. We will look at this in a few slides. The second is the environmental impact. High temperature fields are associated with the emission of potentially polluting gases such as carbon dioxide, hydrogen sulfide and methane. As we have seen, carbon dioxide contributes to global warming. Most of these gases are captured at the point of emission and partly re-injected into the ground. In the case of CO2, this process, which is also widely used in the hydrocarbon industry, is called carbon capture and storage, CCS. Re-injecting gases or other fluids from geothermal plants is obviously something to be done with the greatest care in order to avoid polluting aquifers and posing mechanical threats, as we will see in the next slide. Injecting or extracting fluids from the subsurface has also mechanical consequences, some of which we mentioned already previously. Induced seismicity is probably the most well known. When water is injected, for instance for stimulation, this might reach pre-existing faults. The water under pressure can enter the fault zone, decreasing the stress along the fault and facilitating the slip of the two blocks. This can create an earthquake. Induced seismicity is indeed a recurrent theme in hydrocarbon as well as geothermal fields industry. A detailed knowledge of the subsurface and in particular of the faults and their state of stress is of key importance. On the other side, the scientific community is still far from being able to predict the occurrence of earthquakes. Paradoxically, our incomplete understanding of induced seismicity is documented by the observation that the majority of hydrocarbon geothermal fields are not associated with any above normal seismicity. Despite the challenges and dangers associated with the exploitation of geothermal energy, there is no doubt that it will play a major role in the future in providing part of the energy the world needs. The great advantage of thermal energy is that it is clear and it produces much less carbon emissions than fossil sources. Interestingly, a large part of geological knowledge and expertise you need to develop and exploit geothermal energy is very similar to what developed in the hydrocarbon industry. The two have very much in common. Having a good understanding of geological processes will help you in both. I hope that the GeoMOOC has helped you in reaching these goals.